Okay, good evening. Uh, Today I want us to do the Newton's second law of motion. As you see from the diagram, I have some notes here. So the Newton's second law of motion, it states as follows. It says that when a resultant force or the net force acts on an object, the object will accelerate. In other words, the object will move in a direction of the force, at an acceleration directly proportional to the force and inversely proportional to the mass of an object or of the object. So what do they mean? Mathematically, they mean F net, the resultant force, is equals to ma, or m multiplied by a. That's what they mean actually, or in simple terms. So this statement or this law, you are required to know it and you are required to express it in a form of a formula. But in most question papers, when they ask you state the Newton's second law of motion, you just have to state it as it is. When a resultant or a net force, you don't have to use an or. If you are using the resultant, you don't use a net. If you are using the net, don't use the resultant. When a net force acts on an object, the object will accelerate in the direction of the force at an acceleration directly proportional to the force and inversely proportional to the mass of an object or of the object. That's how it states. And let it be so clearly and simply. And then going further, we goes to what do we mean when we say F net, when we say acceleration, when we say mass. So F net is the force or is the net force act on an object. It's measured in the newtons, capital letter N. It is the SI unit. The newtons is the SI unit. Then A is an acceleration. A, object's acceleration, whatever that is moving at that direction where the force is applied to. An object when it makes a motion or accelerate. And then R is measured in meters per second squared. Or some can say M over S to the power of 2. Then M represents the mass. The mass of an object is measured in kilograms. Every time when you are given this mass, make sure that you convert that mass into kilogram if it was not given initially, so that you can end up calculating correctly. Now, a net force acts on an object. Then an object F net is not equals to 0. It means that there are forces acting which are non-zero. So they say that the net force is not equals to 0 newtons. So the forces acting on the object are not balanced net forces. What do they mean when they say that? Then the forces that are acting on the object are not the balanced net forces. And then they cause an object to accelerate. It's because they cause an object to accelerate in the direction where the force is applied to. And then acceleration and the net force go in the same direction. The acceleration and the force goes in, and the net force goes into the same direction. Wherever the object is moving towards, it is where the force it was applied into. And then there is a change in the velocity, which means the final velocity and the initial velocity are not the same. Therefore, acceleration is not 0. What they mean when they say that the velocity of the initial and the velocity of the final is not 0. If an object moves from one point to another, it means there is a velocity in which that is making the acceleration upon. So it's not the same. So it will reach second point at certain velocity. It moves from one point at certain velocity. They are not the same. Now, acceleration or R is directly proportional to the force net or F net. When the net force increases, the acceleration also increases, vice versa. But then, acceleration is inversely proportional to the mass. When the mass increases, the acceleration decreases. Now, I'll just demonstrate an example here on a horizontal surface. I hope it could make sense. If that's the case, let's hope it will make sense, okay? Let's see. This is an object. This is an object. So an object is on the horizontal plane and it's stationary or it's static. There is no force acting on it. There is no force. When I'm saying there is no force acting on it, I'm lying. But I mean when I say there is no force acting on it, I mean what the object doesn't have a motion. So there should be the applied force acting on it. Automatically, when an object is like this one, there is a normal force that is upon it, and there is also the force of gravity that forces it to goes down. When I take it up, it keeps on going down. That pull is down to the ground or to the surface or to horizontal plane. That's the gravity. Automatically, we have the two forces acting on this object. Okay, now here is our object. Our object automatically, let's assume with this paper is horizontal plane, and then this side is the upwards, and then this side is downwards, then this side is to the left, and then this side is to the right. Let me just label this one simply so, downwards and then upwards. Now, if the object is like this one, and then automatically I am having the normal force acting on the object because it's on the ground, and then I also have a weight, or some can say FG or gravitational force. Now the object is stationary, so if I have to remove this object and work with the imaginary object, which means or wherever there should be an object, I will put a point, or I just put a dot simply so you see the space is too much. I'm trying to put a big circle, but that's where the object is. So now if I use this pen and then horizontally horizontally I push up this object with a certain amount of force, and then I push it to the right, the object will move to the right. That's what the statement is saying on the second law. If I push it to the right, the object has to make a movement, or it has to accelerate to the right. Let's see, if I push it to the right, the object will go to the left or up or down. Now let's try to push it. Unfortunately, this object is my thing is not stable. It might move out of the line. Okay, let me push it to the right. My aim is to apply. This is the force that I'm applying on an object. I apply it to the right. Okay, you see, now the object is moving to the right or towards the right. So which means that the applied force is going to be this side. And then wherever the object is opposing the motion from, which is left, that's where we put the friction. Or someone can say FK. What does FK mean? It means the kinetic friction. If it's just F, you just say it's a friction. But then what kind of friction is it when an object is making the motion? It's a kinetic friction. So when I say FK, I specify. You get the point? Good. Now, which means, Warren, there are four forces acting on this object when it is stationary, static. It is not moving. It is static. It's at the state of no motion. It's at rest. So if it's at rest, therefore, there is no forces that we say, because we say that normal force is going to be equal to the weight. Then it equals to 0 because there is no forces on acting on it. So now when I apply this force to this, why am I applying force from the left and then I write it on the right? Now we write the forces to the direction where it is going, or the direction where we are showing. So if this one comes from the up, this one comes from the down, this one comes from the left, I write the forces to the direction where they are going to. So this is what the demonstration it is. Now I'm going to change the position in which that I have applied the force. Now the object will still move to the right, right? But the force that I'm applying now is not going to be horizontally or parallel to the horizontal plane. It's going to be at certain angle, which means from the point of the block, I'm going to introduce a certain angle here. So if I'm going to introduce a certain angle, I have to see where is the object going. Now the object, I am trying to make sure that it moves to the right. Now let's move the object to the right with this one. Now you see the way in which the pen is and the way in which the object is moving. You see now the force is no longer the same as like this. It's now in this a certain angle. Let's assume the angle is 80 degrees. You see now, So now our applied force is no longer going to be this one, but our applied force is going to be in this format simply. So quick, it's going to be a sorry, no, my mistake. Normal, weight. Okay, this is left, this is up, this is down. Okay, this is my object. I have to introduce the force in which that I was talking about, that it was applied at this angle of 30 degree to the right. It's no longer going to be the applied force on this direction. Now we go to the second direction in this way, where we're going to say, okay, now since the force was coming in this way and then the object was moving to the right due to on the horizontal plane but on the right, therefore the angle in which the force was applied and the direction in which it's going is going in this side, yes. So which means our applied force is going to be in this direction. You get what I'm saying? Not yet. Okay, it's okay. Because it's going to this one, it's going to this direction. Applied force into this object is like this. You see now, this is the object, and then this is the applied force. You see the arrow. You see the arrow. You see the arrow. You see the arrow. Then afterwards, I have to draw a parallel line to this horizon. This is the horizontal plane, right? Then the parallel line is going to be in this way. So if here it was the angle of 30, this angle of 30 is the same angle of this 30 here. So which means it is the same now. Now we will call it the F parallel. So you see where it's coming from. So it's coming from this point where we say it is from. This is the same applied force. Now just that our applied force is going to be in different direction. Our normal force, then our friction, where the object is coming from. Remember, the object is just on the horizon. This is the horizontal plane where the object is moving from this direction going to this direction, but just that the applied force now is coming from certain angle, so I have to suspend it to that angle. So this is gonna be our weight or our FG. So nothing is changing in most cases. So we'll go into this one. I was just trying to demonstrate how the object will looks like. Okay, let's come back to this one. And then going further, they say acceleration is inversely proportional to the mass. When its mass increases, the acceleration decreases. Okay, now here we are having the diagrams that I was trying to demonstrate back then. And then we'll just look at them one by one if possible. Now here we're talking about the horizontal plane. And the horizontal plane, there is a friction, or the horizontal plane is frictional. The diagram, it states that if the diagram is like this one, then we are having the object. This is our object. You see this square or rectangular shape, it's our object. And then this capital letter F here, it represents applied force. This direction here, the arrow, it shows where the applied force is going. It shows where the applied force is going. So now in the first direction, or in the first direct diagram, our applied force will goes to this side. So where is our horizontal plane here? Someone will ask, where is our horizontal plane here? Our horizontal plane is still the same. Is this one. Let me just draw the dotted one. Okay. Dots. Okay. This is our horizontal plane. So which means our force is moving from this side. So our object is moving from, let's say this one is it's left. It's moving from left. Let's assume from left. It's going to where? It's going to right. It's going to right. This is our right side. And then if this is our right side, I'll just simply write the right this side. So this is our right, where the object is moving from. So automatically, where the object is from, it is from this point. So if you can see, this is the point. This is the point where the object was. This is the point where the object is or was. This is, the object is drawn as a rectangular shape. So I'm going to put the point where it is at stationary. Then now the applied force on it, the applied force on it is going to force this direction of the object. It goes to the direction where the force is applied, which means so the force applied is applied to the right, then the object will move to the right on the horizontal plane. So the normal force will apply normally, and then the weight will apply also normally, which is the which is the gravitational force. Then wherever the object opposes the motion from, so this is going to the right, which means to the left, the object force is called the friction. There will always be friction on the surface and then between the surface and the object, as long as the object is on the ground due to gravity or the gravitational force or the weight. Then simply throughput diagram, it will be just simple plus like this one. Then the formula, don't forget that the net force is equal to, now when we say that the net force is equal to, is the same formula that we talked about on that side, then AM or MA. But then on this one, since we said that this one and this one, they gives us 0, then we will say that when an object is like this one, the forces applied on it, then all the forces acting on an object will be the applied force, and there will be the frictional force. So the frictional force is always negative. Why do we consider, or someone can ask, why do we consider frictional force always negative? Because when we take to the right as positive, when we say to the right as positive, to right as positive, and then, which means obvious, what our ring to left will be what? Will be negative. That's how we always get to the answer. So which means what? Now we have to add all the forces acting on an object. Remember, to right positive, to left as negative, or to left as positive, to right as negative. Then it will be depending on the diagram or where the forces applied is going. If the force applied is going to the left, then you assume the left as positive. Then now if we are to add these ones, which means the forces that are going to right, all of them will gain positive. Then I will just write capital letter F, which is as positive. So I will have positive F plus the other force that is acting on it, which is what? The F, small f, which is frictional force, which means is, why am I putting it as a negative and also small? Because it's a frictional one. Then it's going where? It's going at the opposite direction. Why am I putting negative? Because it's going opposite direction to this one. This one is going to the right is positive. Don't forget that. Then this one is going to left. The left is negative. So after you choose that, and then now you'll understand how are we going to, or how do we end up, or how do they end up putting these ones in this format. Then remember, is a net force acting on an object is equal to mass multiplied by acceleration, which is ma. So yeah, that's how you will get to, or we get into this formula. And then don't forget that weight is equals to normal force, which is equal to mg. Let's not forget that. And then going further to the second part, we have the horizontal plane where there's an angle. Also, there is what? There is a friction. So on the same horizontal plane where there's an action, sorry, there's an angle. The angle now, it is inclined at certain degree. Assume, like I said, on the other side, remember the previous demonstration of the block, it was suspended, or it was inclined as 30 degree from the horizontal plane. So now this one, the force is applied on an object, but then where is it going? Is going in the upwards. The force is going in an upwards direction, but the object is still on the horizontal plane. Now there's a great difference coming to this one. It's gonna be difficult or challenging. Let me just demonstrate it again on the second diagram so that everyone can see it. Okay, let's assume that the angle is still 30, right? I will just normally throw the normal force and also the weight and also the frictional force. But then I will wait with the applied. Why am I waiting with the applied? Because now the force, it's somehow. How is it somehow? It shows at a certain angle upwards, but then it's not what we used to. Now let's see. Let's demonstrate this one. Okay, now there is no applied force, but then according to this pen is going to be the direction in which the force applied is. So which the force applied is, it means it's in this way. It can either be a string attached to it, or it can either be something that in this manner, but then pushes it in this angle. You get me? When it pushes it in this angle, but the object is not moving to where the angle it is going. You see now, it pushes it to move this direction of the right, but at this angle. Let me see. You see how I'm holding this pen? Let's see if what I'm saying is gonna be correct. Okay, now the way I'm holding this pen, I'm holding it in this way, and then now the object is still moving. It's still moving to the right. You see, still moving to to the right, but the force is now applied on the object at certain angle. So which means for now the force that is coming, it can be in that way or it can be in this way. Then which means for now it's gonna be the force applied in this way. So I'm going to have my capital letter force applied in this direction, and that is my free body diagram. This is my object. This is my object. Friction, where is it coming from? So in other ways, this is the horizontal plane. You get it? This is the horizontal plane. And then in this horizontal plane, then we will make our triangular shape. Our triangular shape is always 90 degree. Then this side we will have X, this side we will have Y. And then again, we'll also have F parallel, which means we will have what? We will have this dotted line according to this one. And then still, we will still consider our shape. You can still see the triangle, so which means if the angle here it was 30, and then the same angle here will be 30, because this line is now parallel to this one, because it's horizontal plane, the parallel line, and then the force also is parallel to the horizontal plane. So that's why we call it F parallel in most cases. So you'll get to understand where we talk about the Fy and also the Fx maybe in the next topic, but then we mostly introduce them during the way, because there is no specific part where we do that. So let's go back to the next part. The next part, we see horizontal plane at an angle. It's the same thing, frictional, but then now it's coming from the top. You see the force is now coming from the top. Now if the force is coming from the top, it's going downwards, but then the object is still moving to the same direction, horizontally. That's what we want. That's what I have. These statements are very important in your questions. If they say horizontally, then don't forget to do that, to throw that parallel line horizontally. So what do I mean throw that parallel line horizontally? I will just say on my object, okay, this is my object, this is my free body diagram, okay, this is my object. But before you see the object here, the object here is drawn, and then the parallel line Q. This is the horizontal line. This is the horizontal line, and which means the object will move from let's say, yes, the object will move from left to right. From left to right. Yes, the object will move from left to right. Let's see how it will move from left to right. You see now, but then the force that is applied on an object, it's not from left to right. It comes from certain angle. If the same angle is 30, or it can be 45 or 20, or any amount of value that they give you in a degree, then you also have to accept it, and now take it in this perspective that the object will still move in a horizontal plane. Even the same horizontal plane, left to right, we can still write it here on the free body diagram. The object, it will move from left to right, but the force acting on it is coming at a certain angle. So the forces from here and also here is still the same thing, just that this one is coming from the top to downwards. Then you see how the free body diagram is drawn, and then on this one we are saying that now all the forces acting on it, it's also what, the F parallel, or the same applied force, and also what, and also the friction. Don't forget that the friction is minus, which is this one. So why do you say the minus? I tried to explain this one, and therefore now we are going to this way. Since now the force parallel and the force perpendicular, force parallel is and force perpendicular, they are on the same part, therefore weight and perpendicular, they must give us the normal force when we add them. These three things are almost the same. These three parts are almost the same. Number one, number two, number three, they are almost the same. So what I played with you, Goring, all of three of them, they are on the horizontal plane, just that the force comes in different angles, and also in different directions, but moving on the same direction, from left to right or from right to left. It depends on the statement and also the question. What does they want at that moment? So be careful when coming to that ones. Be careful. Sorry for that. When I press the numbers, they also changes into the scenes. So if you couldn't catch up what I was talking about, sorry about that one. But then in this manner, here we are. Here we are. Let me just give you a minute to check us through. Okay, good. Let's go to the next one. The vertical. Now the object is coming from, or the object is on the vertical. Remember, vertically is the same. It's more, it's when we say the object is more like in a, when coming to mathematics, y-axis. So the object is, in most cases, since there is no gravity that is applying on it, in the form of it's on the surface. When I say no gravity applying on it, it means it's on the form of no surface. Now this is where we talk about what goes up must comes down. If the force that is now acting on the object, it's more than the one of the gravity itself, therefore the object won't go down, it will go where the force applied to it, it will go. Now this is where we're talking about the object attached to a certain string. And if the object is attached to a certain string, it means soaring. Now we're talking about the type of force, which is the type of force exerted called the tension force. We'll be talking about tension force. You'll no longer be seeing the normal force in this way. So not normal force. Yes, normal force, and also the F parallel or the F perpendicular. But here we'll see the tension and the weight. So in this question, here we are. This one is very simple. I also fail to explain the simple things in my nature. So this is the object is given. So this object that is given here is attached to a string. This is the string we see. And then this is the horizontal plane. The same horizontal plane we've been talking about, the same one. This is the horizontal plane where it is going to go into. And therefore, if it's going up, if this is the horizontal plane, let's just draw my dotted horizontal lines. Therefore, the string is going to pull this object, in most cases, is to pull the object back into the horizontal plane. So which means there is a force acting on this object, and the force that is acting on this object is the force of gravity, or someone can say it's a weight. You see? Yes, and then now the force that is attached to a certain thing, we call a string and or whatever, we call it a tension. So this is the type of force that is acting on this one. It's a tension. So looking at the diagram of the force, we have the tension and the weight. This is the object. It's not on the horizontal plane, it's suspended. Maybe from the table, facing downwards, but not on the ground, not on the table. But the string maybe is on the table, attached to something or else. Freiburg diagram, simply, there is no normal force here. There is no friction as we see. So the force net or F net is equals to MA, so which is equals to weight minus T. Depending where is it going, weight minus T. Some will have T minus W. Then the last one, it's inclined, this one. When it's inclined, it's frictional also. There's a frictional force. So now it means, or now the object is no longer moving on the horizontal plane like the Earth's surface. Among the Earth's surface, there's another surface that is not the same direction of the Earth. So it's gonna be going up, maybe going up to at a certain slope, going up to the steep or the hill, or going down from the hill. You see, it's not so it's not parallel to the Earth's surface, going up the hill or going down the hill. It always feel like you are falling, or it feel like you are coming down. That's how these forces are. And this how now the object is certain degree like that. Degree I'm talking about, the angle is suspended at that certain angle. And then after it's suspended at that certain angle, now the force is now going to, is applied. Now it's applied, and when it's applied, if it's applied going up the hill, it means soaring. There will be friction, which is one that pushes it down the hill. But the object keeps on going high because the higher up the force applied is higher than the frictional one. Then weight is always weight to the Earth's surface, horizontally to perpendicular to Earth. Yes, perpendicular to Earth's surface, always the weight. But then the normal force is always perpendicular to the surface we are talking about. but not the earth surface. If it's the earth surface, we'll go back to diagram 1, 2, and 3 if you still remember. That's the earth surface. The normal force has to be perpendicular to this surface that we're talking about. So now this is the new surface, but not the earth surface. So remember, or in this one, the earth surface will be this one. This will be the earth surface. So you see the triangle that I'm drawing now. Is a triangle that I'm drawing. This is the earth surface. The weight is always perpendicular to the earth surface. That is why it's in this direction. But then the normal force is always perpendicular to the surface of where the object is. Don't forget that. It's always perpendicular to the surface of where the object is. This is the normal force. Then where the object is going, that's where the force is exerted to. That's the second law. You'll never go wrong with the law and applying it. Then where is coming from? It's friction. Simple free body diagram. Then F net is equals to MA. Then here we are having the frictional force acting on it, then the weight also acting on it. Then that's going to be weight parallel. Why is it weight parallel? Because there is another weight that, or if you see, this one are the dotted forces. This is the weight parallel we're talking about. So this one, when we throw the horizontal line to this surface, it's going to give us something like this one. The line, just that this one can throw the horizontal, it's going to be parallel line to this horizontal line. Then it's going to be something like this one. So we'll be talking about the same way that we're talking about. So it's F minus into brackets friction plus weight. So remember, weight, this weight, it's weight parallel. Why is it parallel? Because it's inclined at certain degree. So we also have weight perpendicular. So weight parallel is the one that goes with sine angle, and then weight perpendicular, it goes with cos angle. And don't forget that always the weight is equal to the normal force. Here we are. So those are the angles. Now, with the knowledge of this free body diagram or diagram of the forces, every question paper that will come will be based on this one. And these are the basics from grade 10 and 11. Specifically, these ones are for grade 11. So with every question that comes, you will see the diagram drawn, one of these four. I'm telling you, one of these five. I'm telling you, you will never go wrong with understanding this and seeing the diagram. Now, let's look at as any question. See, now I'm looking at question 7. I have underlined question 7 here. And also there's a question 8. There are a lot of questions from 1 up to hundreds of questions. But then let's just look at this one, number 7. If you can look at diagram of number 7, we are having object with 1.5 kilograms, an object attached to objects due to certain string, the object which is 3 kilograms. So now the force applied to this object of 1.5 is the force applied from this angle of 30. So which means the object, you see the arrow means or it goes to this direction. Therefore, the force will have to go where? If I may ask, the force will have to go where? The force will have to go to the right. So this is the direction in which the force is going. So the object is on the horizontal plane, which means it's going like this one. So if I have to draw my free body diagram on this one, so let's assume this one is the, okay, on the 1.5 kg block, okay, this is my arrow showing that this one is going this side. It's horizontal plane, okay? And then if I have to, okay, remember, as in this way, I don't have to put this side first. I will finish with the applied force, okay? This one will be my friction, my frictional force. Since it's moving, I will say it's kinetic friction. And then this side, I will have my weight downwards. I will have my weight, and then upwards, I will have my normal force. Why not perpendicular to this angle? Because the object is moving on the horizontal plane, and the horizontal plane is parallel to the surface. So there is no need. So you see the object. Okay, let me try to draw the straight line this side so that they can two match. Okay. Good. Now, where will be our applied force. The applied force has to be same direction where it's applied. So which means from the object, I will draw a line in this way. Okay, let me try to move it up next to the, so that it can fit. Okay, let me remove this one because it's eating my space. Good boys. Okay, now that's the free body diagram. And this is, don't forget that on the free body diagram, we label the forces. If you don't label, there's no mark, because if it's 4 marks, then it means all the forces acting on it, this is the force applied, or someone can just leave it as F. But then now this object is not finished. This object of 1.5 kg is attached to another object due to string. And when an object is attached to something due to a string, that force, we call it a tension. Don't forget that. That force is called a tension. Now, the direction in which the string is, that's the where you have to put the tension. No matter if you have force already or not. So you already have F kinetic, then I will put the F tension on that side, smaller or longer. So that's the free body diagram. So which means the free body diagram of this question has to be 5 marks. Let's see if they're looking for 1.5 kg, 3.2, on 3, sorry, 7.3. I'm reversing things now. 7.3. Here is the 7.3 question, and the marks are 5. 5 out of 150. Hey, so not 3%. Okay. It says that draw a labeled free body diagram showing all the forces acting on the 1.5 kg block. Simple. After you read the question, look at the marks. That's the tip. Look at the marks. Look at the marks. Ashley, look at me. Yes, you. Look at the marks. Look at the marks. Look at the marks. If the marks are 10, it means all the forces acting on the object are 10. But if the marks are 2, it means all the forces acting on the object are 2. But if they are 3, it means they are 3. So if it's 4 like this one, or 5 like this one, it means they are 5. So it's a win-win situation. It's a tip that you must go on with. Okay, good. It means, or I will have 1 mark for each of these diagrams. So if I'll have 1 mark of each, according to the marker, I'll have 1 mark for free, for normal, for applied, for weight, for tension, and for kinetic. Then it's 5. So there is nothing you will lose. From this one, what I mean, there's nothing you will lose. All the calculations will come from here. If it's a 1.5 kg block, you already know this is a applied force on it, and this is the friction, and also has the tension. So you will never know. You will never forget. Warring F at certain angle. Minus tension, minus friction. There you are. Why are we saying minus tension, minus friction? Because there is 2 forces opposing the motion. So the value FA plus, minus into brackets tension plus friction, Fk. It's equals to MA. And don't forget that this one is certain angle. So if it's certain angle, it's going to be that certain angle. So we're going to have a force like this one at some instances. But then we're not there. It's just the force applying. I'm just trying to demonstrate. So if it's a 3 kg block, the free body diagram of the 3 kg block, so which means for this whole system, I haven't read the statement, but it's interesting due to knowing how to draw the free body diagram. So I used to teach my learners that when we see the diagram, or when we see the statement, hide the questions and deal with what you see in the diagram and also the statement. And then afterwards, look at those stupid questions. Now, the free body diagram of this one, what do I mean? When I say look at those stupid questions, you'll understand. Okay, always there is weight. Always there's normal force. And then since that this applied force is now attached, it's coming as a string. It comes as a string. Okay, it comes as a string, so which is this way. So it's no longer gonna be FA or capital F. It's gonna be the tension. So coming from this side, it's where is it coming from? That's the friction. Okay, now let's see. Let's label FK. And then normal force. The weight. And then someone can put force and you'll get wrong. Unless you put FT. And if you are your teacher for physical sciences is clever enough, will know what is FT. But if then they don't know what is FT, they will always looking for you or from you to say right tension, as if they are always right. But then we are not there. This is tension. And tension is the type of force that is exerted on this object. If the object of 1.3 is moving to the right, the object of 3 kg also move to the right due to attached to an insensible string or whatever. So let me come back and not drop you. Let's read the question. Sorry, the statement. Elena construct a push to... I'm not good in English, but reading it's my things because I'm from England. Elena construct a push toy using 2 blocks with masses 1.5 kg and 3 kg respectively. There is always an English that is important, and if you fail to read its importance or see its importance, then you will fail to understand. Okay, now the blocks are connected by the massless, which means it doesn't have an effect, inextensible cord or a string. Okay, the learner then applies a force of 25 degree, so Newton, at an angle of 30 degree to the block 1.5 kg by the means of light rigid rod. Why they say light rigid rod? It means it won't have impact of increasing the mass on the object. It won't have impact in the acceleration, but only the forces, only force exerted or applied to have an effect, causing the toy to move across a flat rough meaning or there's friction. Automatically we have drawn the free body diagram, we have seen the friction. When they say flat horizontally, we go back to horizontally. Rough, it means friction, then horizontal surface. So you see, they are given a lot of information here, and then they want you to fail at the end of the day. No one is looking for you to fail. They know these questions looks different and looks difficult, but then if you can understand how to deal with them. What do I mean to deal with them? This is the part that I want you to deal with them. I want you to deal with them in this section of drawing the free body diagram. So if you can know how to draw a free body diagram, I'm telling you, you are a genius. Okay? Then the coefficient of kinetic friction, which is represented as the UK, between the surface and each block is 0.15. So which means the block of 3 kg kinetic friction applies. Coefficient of it applies, block of 1.5 kg, the coefficient of kinetic friction also applies on it. So we can use it onto any of the two. So let's get into details. Then how do we win here? The first question says what? State the Newton's second law of motion in words. You know it. If you don't know it, then you are wasting our time teaching you. 7.2. Calculate the magnitude of the kinetic friction. force acting on the 3 block. So kinetic friction, it means soaring. There is a movement. There is what? There is a movement. And don't forget that the formulated formulas, now they will lead us here, saying that the FK will be equals to, let's represent U, that thing by U. Kinetic friction multiplied by the normal force. Okay? So that's the formula. So if that's the formula, we know that the normal force is equals to weight, you know? And don't forget that. And you write it somewhere, N is equals to weight. And what is the formula for weight? Weight is mass multiplied by the gravitation. Gravitation. Acceleration, 9.8. Okay? So now we talk mathematics. Simply, we will be having something like Fk is equals to 0.15 into brackets mg. Mass of what? What's about mass of what? 3 kg, which will have 3 multiplied by 9.8. So if you have a calculator, this will give us the answer. Okay, let's go into my writing pad. My writing pad is not nice, but let's go into my writing pad and forget the computer for a while. Okay, from here, okay, we're having Fk is equals to the coefficient of kinetic friction multiplied by the normal force. Good. Okay, whereas the normal force is equals to the weight, which is equals to mg. Write it somewhere because it will give you the mark, or you can write it below, and it's equals to w, which is equals to mg. Therefore, we'll have Fk, which is equals to the coefficient of kinetic friction multiplied by mg. And I'll have the kinetic friction, let me substitute 0.15, all of them in the brackets, 3, 9.8. Okay, if you have a calculator, it gives you the value. Remember, this is also a force, and force is measured in newtons. So if you have a calculator, it has to give you 4 comma something. There's a comma here, don't forget that there's a comma here. It has to give us 4 comma something, 4 comma something, and the calculator is 4.4 newtons. So our Fk, that's the answer. So that's how we arrive to the answer. And so quick to the answer. Okay, next question. We skip 7.3, we go to 7.4. It says calculate the magnitude of the following. The first one. Okay, let me get rid of this one. Okay, now since we know Fk, don't forget that we use the previous answers as much as possible. It's more like mathematics when you solve something. So here the answer is 4.4 newtons. Okay, then we will go to the next question. On the next question, it might be possible that we need to use this one, but it will depend on what the question is looking for. Okay, and then we go to next question. The next question says the kinetic frictional force acting on the block of 1.5 kg. Kinetic frictional force. You see, where is the kinetic frictional force? You see it. So, like I said, we are having forces that are acting on the object there. So we have to look into those forces and then see how we can relate into 1.5 kg block. Okay. With much being said, the object, the force applied is at a certain angle, which is 30 degrees, if I'm not wrong. And then we'll still use the same formula, which is Fk is equals to kinetic coefficient of kinetic friction multiplied by the normal force. You remember that formula? Yes, it is. And now the normal force, let's not forget that the normal force, now we have to look at all the forces acting on it. We said that the normal force is equals to what? Is equals to weight. Where? We said is equals to weight on the object. On the object 3 kg block. This is 3 kg block, and 3 kg block is on the horizontal surface, and this is the first force that is exerted on it by a tension, and then this is the kinetic friction, then this is the weight, then this is the normal force. So you see, this is the first diagram that I've shown you that side there is no effect, so there is no any other force. So now on the 1.5 kg block, on the 1.5 kg block is different. It's gonna be different. Yes, sorry, I'm just stripping here. So we will have our weight here and our normal force here, and then our force exerted in this direction, which is now the force applied, capital F, and then we will have our tension and also the Fk. So this Fk is not the same Fk as this one. This Fk and this one are not the same, but the coefficient of this kinetic friction is the same, which is 0.5. That's what the statement has told us. So which means now the forces that were acting here, if we were looking for this one, on the normal force is equals to weight. So there is no any other forces in between here. It's just this one, and this one is equals to this one. Let's not forget that. Whereas we know this one is equals to this one times the coefficient on it. So here we are having another force here. This is the force, and it's inclined at a certain angle. So that certain angle inclined into that angle is what? Is 30. Is what? So it's 30. So I'll draw the horizontal line for it to a surface that the angle is 30. Is 30 degrees. So which means wherever I see this force, I will put sine 30. This is the force. I will put what? I'll have to put sine 30. Why do I have to put sine 30? Because yes, that's it. And what will form normal force here? The normal force will be formed by this, which is what? Which is the force that is applied there, and also aiding with the what? With the weight. This will be equal to the normal force. Why? Why are you saying this, Minier? Because the applied force is equals to the normal force minus the weight. So if one does to work with the formulas and do the formulas, we will spend the whole night working with the formulas. Okay? Let's get into details then. So which means we're going to talk about these ones. So we already seen our part. So we will say that this one is equals to F sine 30 plus weight, which is mg. So we will have 25 multiplied by sine 30 plus 1,5 multiplied by 9,8. My space is lost. Sorry about that one. So why am I saying that one? Like I explained, so let it be easy for understanding as I have explained. So due to space, okay, let me add more pads. We said Fk is equals to coefficient of friction, normal force, and then which is equals to F sine 30 plus mg. Okay, so don't forget that this is normal force. This is normal force. This is normal force. Then we'll have Fk is equals to 0,515, sorry, multiplied by 25 multiplied by sine 30 plus 1,5 multiplied by, let me put the brackets, 9,8. So which must be inside here. When you substitute on a calculator, let me see, what do I get when I put on a calculator? Quickly on the calculator, on a calculator. calculator. Okay, I'm getting 2 decimal place, don't forget, is the final answer. I'm getting FK on the block of 1,5 kg, which is equal to 4,08 newtons. You see, now we use what we have, or we use what we are given to understand. So, which must be said, I would like to cut off the video here. So here we have FK. FK is equals to 4,08 newtons. So we might use these answers in future. The last question, tension, calculate the magnitude of the tension in the cord connecting the 2 blocks. So they want the value of force T, or the applied force to 3 kg block, which is the tension, or the frictional force acting as a tension on the block of 1,5 kg. So they're looking for that. So in other words, you will start with the 1.5 kg block or 3 kg block. It's up to you. I'll just give a hint on how you do it. So on the 3 kg block, we will have forces acting on it, which is now we're having tension minus the FK. Tension minus the FK, which is equals to MA. Which is equals to MA. So the value of the tension is unknown. The value of FK, we know it is 4,41 newtons, is equals to value of mass is 3. And then what else are we looking for? Okay, we don't know the acceleration that it used. Okay, let's just put the unknown acceleration. Okay, then so far we'll wrap it up. We'll say T is equals to 3A plus 4,41. Okay, this one needs the mathematicians. I'm trying to formulate the formulas here. And then the second one, on the 1.5 kg block, on the 1.5 kg block, we will be having something like, hey, it's quite tricky, this one. On a 1.5 kg block, we'll be having something like, okay, don't forget that if you don't know the formulas, start with F net is equals to MA. So they will give you mark. Even if the second one is wrong, this one is correct, they will give you the first one, which is correct. Okay, we'll be having let's have a free body diagram so that everyone can understand. Okay, let's use this one. Here we are having the angle 30. So this side, this will be our Fx, and then this side, or also going up, will be our Fy. So we are looking for this part. This is on the horizontal plane, right? So our now F applied is going to be named as our Fx. That's how you should understand it. So I will have our force plus tension. Tension, remember, is more like it's more like a friction acting on this one, because it goes to opposite direction of the applied force, so it's gonna get negative. Don't ask me how, because I just explained. And then also with what? With the frictional kinetic friction, also is on the opposite direction. So in other words, one can say this one is equals to, Fx, our Fx plus, our Fx minus into brackets tension plus Fk. This come from the same group again. Remember, they were acting opposing the applied force from the free body diagram. So we have this one. Now this one, since it's x, it goes with cos, not the sine. Don't forget that. Or we can use the one that we used on the previous one of sine 30. It's gonna give us the same value. So we'll have 25 multiplied by cos 30 minus into brackets t we don't have the value. FK, we did calculate this one. It gave us 4,08. Then mass is 1,5 kg. We don't know the acceleration so far. Now let's work out with what we have. So working out with what we have, this one will gives us 12,5. Something like the commas. Hey, I'm not sure calculator. Okay, let's punch the calculator. And then it's more like this one minus this one. And then will give us something like, okay, this one minus this one. Okay, let me just rewrite this, because some of you don't understand, and you're not willing to understand if we skip the step. Okay, and then from this point I extend it further to here. We will have something like 25 cos 30 minus 4,08 minus t is equals to 1,5 r. Okay, on a calculator. Remember, it's not the final answer, so we can write all the values that are coming from here, all the values that we get, or write it in a form of a fraction if you get it in a fraction. So minus the t, then we'll take this one as equation number 1, and then the other one that we solved of 1.3 kg, we say is question number 2. Is up to you which one do you take as equation 1 and 2, and then you substitute, and then you will get the values of r. Then after you get r, you come back here, you solve for t, let it nazo. So that's how we kill it. Remember, I said that I'm not going to show you the answers, but I'll guide you how we arrive to the answer. So this is how we work it out. The first part, you do the 3 kg blocks, all the forces acting on it that are not resulting in it being 0. Being 0 meaning warring does not move. So this is the forces acting on it. Normal, weight, because we included them here, they take effect on this part. And also here we have this 1, 2, 3 forces acting on it. So yeah, let's look at it. And thank you very much for your cooperation. If you have any question, just comment, and then we'll look into more questions. But before we finish up, this is the key part of it. This is where life starts. This is where life starts. Please try to understand these things and try to relate them to every diagram and know what you are looking for, what you do, what will you do when you see and find the questions. Thank you very much.